Hello, I am Ikshita Ghosh. Currently, I am working as an assistant professor in EC department at SBIST. So, today our topic of discussion is the analysis of half-wave rectifier. So, in the previous lectures, I have discussed about the working of the half-wave rectifier where we can see the only half portion of the input wave is rectified. So, in that case, first the point is input voltage to the rectifier. We are assuming that voltage across the transformer secondary sinusoidal of peak value, which is Vp. So Vp is the peak input voltage and the instantaneous voltage applied to the rectifier is Vi, which is equal to Vp sin omega t. Okay, so we are neglecting the diode cutting voltage, which is much less than that Vp. Now the next point is the current through the diode. In that case, we have considered that the diode has a forward resistance RF and a reverse resistance RR, where RF has a very small value and RR has an infinite value. In that case, the current flowing through the diode is given as ID, which is equal to Im sin omega t, that is for from 0 to pi range, and after that it is equal to 0 because it is in the negative half cycle portion, where Im is the peak current which is flowing through the diode, that is equal to Vp by Rf plus Rn, where Rf is the diode forward resistance and Rn is the load resistance. And the next point is peak inverse voltage. First we have to know what is peak inverse voltage. It is the maximum voltage that is applied across the diode when it is in reverse biased mode. So in case of half wave rectifier, during the negative half cycle of the input voltage, the diode is in reverse bias mode, and in that case, no current flows through the load resistance, and so there is no voltage drop across the load resistance. So the whole input voltage appears across the diode. Thus, the maximum voltage which is appears across the diode is equal to the peak value of the secondary voltage, which is basically Vp. So, in case of half wave rectifier, the PIV, which is peak inverse voltage, is equal to Vp. In case of full wave rectifier, this will have another value. Next, we are discussing about the DC value of current. The DC value, that means the average value of output current, is given by the value IDC, which is equal to 1 by 2 pi integration 0 to 2 pi ID d omega t. Now ID is the diode current, which is previously shown Im sin omega t from pi to 0 to pi, and it is equal to 0 from pi to 2 pi. So in the next line, we are segregating the 0 to pi and pi to 2 pi, and we are considering only 0 to pi value because pi to 2 pi range ID is basically equal to 0. In the next line, we can put the value of ID, which is Im sin omega t, and after calculating the integration, we have IDC equal to Im by pi. From this, we can find the DC value of voltage also, because we know the Ohm's law where V equal to IR. So VDC is equal to IDC into RL. Now IDC equal to Im by pi. Just multiply with RL. We have VDC. Next, RMS value of output current. The full form of RMS is root mean square value. So RMS value of current flowing through the diode or load resistance is given as IRMS, which is equal to root over of 1 by 2 pi 0 to 2 pi ID square d omega t. Now, where RMS, first we have to square the diode current, then mean, and then root. So it is equal to root over of 1 by 2 pi 0 to 2 pi ID square d omega t. In the next line, we are similarly have 0 to pi and pi to 2 pi, where pi to 2 pi range it is equal to 0. So we are considering only 0 to pi range and just put the value Im sin omega t after the normal integration, and we have IRMS equal to Im by 2. Similarly, we also have the RMS voltage of the RMS value of the output voltage, V equal to IR. So VRMS equal to IRMS into RL, and we get the RMS value of voltage also. In the next, it is efficiency of half-wave rectifier. So it is defined as the ratio of the output DC power and input AC power. So first we have to calculate the input AC power, which is equal to 1 by 2 pi 0 to 2 pi instantaneous power d omega t. Just put the values, and we have PIAC, which is equal to RF plus RL IM square by 4. We know the value of IM. Next we have to calculate output DC power, which is PODC. Previously it is PIDC because it is input AC power, and this is output DC power, PODC. This is the DC power delivered to the load. So it is IDC square into RL, and we know the value of IDC, which is equal to IM by pi. So PODC equal to IM square RL by pi square. Now we have to find the rectification efficiency, which is equal to PODC by PIAC. Just put the value, and we have 40.6 RL by RF plus RL percent. Now we are considering RF is much less than RL. Why? Because RL is the load resistance and RF is the forward biased resistance of the diodes, which is practically a small value, but ideally it is equal to 0. In practical cases, so RF is much less than RL, and in that case eta is equal to, or rectification efficiency is equal to 40.6. So obviously it is the maximum possible efficiency for a half-wave rectifier. And this is the ripple factor. In case of half-wave rectifier, we have pulsating DC. The pulsating output of rectifier can be considered to contain a DC component and a AC component, which is called ripples. The ripple current is undesirable and its value should be smallest possible in order to make a rectifier very much effective. So the ripple voltage or current is measured in terms of a ripple factor, which is defined as the ratio of the effective value of AC component of voltage or current present in the output from the rectifier to the direct or average value of the output voltage. So this is the R equal to IRMS dash by IDC or ERMS dash by EDC, where IRMS and ERMS are represented by RMS of ripple current or voltage. So first we have to find the ripple current, which is equal to ID minus IDC, because ID is the diode current minus IDC is the DC component of the output current. So by subtracting it, we can get the ripple current, and from this we have to find the RMS value of this ripple current. So this is root over of 1 by 2 pi 0 to 2 pi ID dash square by omega t, and by putting the values and using the last equation IDC and IRMS, we have I dash RMS equal to root over of I square RMS minus I square DC. So by calculating this, we have R equal to 1.21. This shows that the RMS value of ripple component exceeds the DC component at the output of half-wave rectifier. Thus, the half-wave rectifier is relatively poor device for converting AC to DC. So these are the some analysis of half-wave rectifier. Okay, thank you.